Hello everyone, my name is Elisabeth Spiraki from geoengineer.org. I am pleased to introduce you to February's 2017 online lecture organized by the International Society for Soil Mechanics and Geotechnical Engineering. This month, Professor Schweger will be talking about an introduction to numerical modeling in geotechnical engineering. Professor Helmut F. Schweger is head of the Computational Geotechnics Group at the Institute of Soil Mechanics and Foundation Engineering of the Graz University of Technology in Austria and has over 25 years of experience in developing and applying numerical methods in geomechanics. He obtained his PhD from the University of Wales, Swansea, UK. His main research interests are the development of multi-laminate models for soils and the assessment of the influence on the constitutive model for solving practical problems, in particular deep excavations, deep foundations and tunnels. Application of numerical methods in accordance with the design approaches defined in Eurocode 7 is another topic he is involved in. His group was a member of several research projects funded by the European Commission. His research is reflected in more than 200 publications in international journals and conference proceedings and invitations to keynote and plenary lectures at international conferences on soil mechanics and computational geotechnics. He serves on a number of editorial boards of international journals, and he was chairman of 6th European Conference on Numerical Methods in Engineering. As a member of several committees, Helmut is involved in formulating guidelines and recommendations for the use of finite elements in practical geotechnical engineering. In 2005, he received the Excellent Contributions Award Regional of the International Association for Computer Methods and Advances in Geomechanics, the Best Paper Award of the Japanese Geotechnical Society, and in 2010 the George Stephenson Medal of the Institution of Civil Engineers, London, UK, for a paper published in Geotechnic. At present, he is the president of the Austrian Society for Soil Mechanics and Geotechnical Engineering. Note that after the completion of the webinar, Professor Schweger will be happy to answer any questions posted in the ISSMGE Q&A platform. The platform will remain active for 2 days. It is located below the present video and you may access it with your GeoWorld account. Enjoy the lecture.
Welcome to this webinar of the ISSMGE on numerical modeling in geotechnical engineering. This is supposed to be an introduction, and therefore I will address our younger colleagues and not so much the numerical expert. I will also concentrate on practice, so I will not talk about research. The outline of the presentation is a short introduction into numerical modeling, then some aspects of specific aspects we have to deal with in geomechanics, a short note on constitutive models, and then I will present an example for an SLS calculation and for an ULS calculation. And then I will come up with some final remarks. Now, what is the main goal of numerical modeling in geotechnical engineering? Now, first of all, I would say it's understanding. Understand the behavior of geotechnical structures. But of course, we also want to calculate displacements under working load conditions. We want to work out internal forces which are necessary for the design of structural elements. And we want to identify possible failure mechanisms. We can do this when we have appropriate geotechnical models, a very good understanding of soil mechanics. This is sometimes overlooked when people do numerical analysis, that the basics of all of what we are doing is soil mechanics. To understand, of course, what the software and in particular the constitutive model does, what we are applying, and that we have a clear picture what we can do and what we cannot do. So please be aware that we do models, we don't do reality. And as an example, I have a picture here of a deep excavation, how it looks on the computer and how it looks on site. and the same for a big cavern. And of course, this is just to emphasize that we can never picture the situation inside one-to-one into a computer. The scope of this lecture is now to make you aware of specific problems we have in numerical modeling in geomechanics, which are different to, let's say, structural engineering or mechanical engineering. Give some guidelines on the requirements for constitutive models for certain classes of problems like foundations, excavations. Address determination of input parameters, not going into much detail of that, but just highlight a few of the difficulties we have. And point out some of the decisions you have to make when creating a numerical model for a particular problem. And now on the way we go, I will try to highlight some pros and cons of numerical modeling. I'm not covering in this lecture numerical methods in detail, so the theoretical aspects of it. I'm not going into plasticity theory, although the majority of constitutive models we use in practice are actually based on plasticity theory. This is not necessarily the case for some more advanced models, but in practice, in commercial codes, I would say most of the models are based on plasticity theory. I will also not describe constitutive models in much detail, and I will not go into advanced topics like geotechnical earthquake analysis, liquefaction, installation processes, dynamics, and so on. And I will also not cover the topic of how to arrive at a geotechnical model. That means how to arrive establishing the soil profile, description of soil layers, etc., etc. Now to start with, I want to make a comparison between what I call here a conventional approach in geotechnical engineering and computational geotechnics. Now, conventionally what we do is we analyze the serviceability limit state by some simple means like taking models based on elastic half space or some diagrams or design charts, and the input parameter is some form of stiffness, let's say the one-dimensional compression modulus for a settlement analysis. And then we do an analysis of the ultimate limit state, which is a completely different model, and that is what we usually do by means of, for example, methods of slices, if we do slope stability analysis or other limit equilibrium methods. Here, of course, the governing parameters are the strength parameters, and that is effective friction, cohesion, or the underhand shear strength. Now, these two models and also the input parameters, they do not interact at all. These are two complete separate analyses. And that means that we have to significantly simplify the material behavior and to some extent also the geometry. Now the advantage of this is that we have several decades of experience, but the disadvantage is certainly that for complex soil structure interaction problem, a realistic assessment of displacements for working loads is not really possible. Now on the other hand, if we do computational geotechnics, we can use very advanced constitutive models. That means we also will work out deformations and displacements under working load conditions. But now, instead of moving to another model, we can use the same model to work out ultimate limit state conditions. That means we will obtain a failure load or a failure mechanism. Now you can do this in different ways, and if you have a foundation, you probably simply increase the load until you will reach failure. Or in other cases, you may reduce the strength of the soil until you reach numerical failure. And from that, you can then work out your factor of safety. Now the key issue really here is that you can use the same model as for serviceability limit state. And also the parameters are not that clearly separated anymore, so because your strength will influence serviceability to some extent, and depending on the model, also stiffness will probably have some influence on ultimate limit state. Strictly speaking, we could also do post-failure behavior, where I mean that you have materials which show softening behavior, but I have to mention that you have to enhance your finite element formulation for doing so in order to get mesh-independent results, and this is beyond the scope of this lecture today. Now, the advantages of this approach, I mentioned this already, is of course that you have one consistent model for SLS and ULS, but the disadvantage is that it is computationally more demanding. You may have some troubles in getting all your parameters you need, and you may in some cases encounter numerical difficulties. However, if you embark on a numerical analysis in geotechnics, you have basically two classes of methods. The first one is based on continuum mechanics, so that's the finite element, for example, the finite difference method, or the boundary element method. And then you have methods which are based on discontinuum mechanics, and this is, for example, the discrete element method. Now I will concentrate today on the finite element method, but most of what I say will equally be valid for the finite difference method. Now, what are the main problems we solve in geotechnical engineering? Now, first of all, we want to have, as mentioned before, displacements and stresses under working load conditions. So we apply a load, and that can be very general, also an excavation or whatever. And we may solve a flow problem. So we apply a head and obtain a flow pattern. And in some cases, of course, we have to couple the two. Now, what we would like to have is a solution in any point of our project, but that is, of course, not feasible. So we do what we call a discretization. So we divide our domain we want to analyze into so-called finite elements, and we actually solve, or we obtain our solution only in certain points at the nodes of these elements. And then we make some assumptions how our primary variable, which is in a mechanical analysis here in a simplest form the displacements, and we make some assumptions how they vary over the element, and usually we do this by means of a polynomial. This implies that we can have different forms of polynomial, which means we have different finite element types. And in short, the higher the number of nodes, or the higher the order of the polynomial, the more accurate the results will be. Now, what is important to see here is that the solutions we obtain are not the exact solutions, but these are approximate solutions to the boundary value problem we are solving. And of course, the better the model, and I put here model under quotation mark, is not only the element, it is really all our modeling assumptions we have to make, and I will come back to that when I show the example. The better the model, the more accurate is the solution. However, for a real boundary value problem, we will never know how far away we are from the exact solution, because for a real project, a complex real geotechnical project, we do not know the exact solution. But that doesn't matter. I think we just have to make sure that we make a good, appropriate model, and then we will be close enough for any practical purposes. Now, coming to some specific aspects we have to consider in geomechanics, which we do not have, let's say, in structural engineering or in mechanical engineering. Now, first of all, strictly speaking, we have to choose the domain we are going to analyze. a priori we cannot say how far the influence into the surrounding ground of an excavation of a tunnel will be. Of course, we have some experience and there are some guidelines how large your domain has to be, but it is different, let's say, from an analysis of a bridge where you exactly know your structure. Now, for the same problem, you also have to be careful, because whether you do a drained analysis, an undrained analysis, a seepage analysis, or a dynamic analysis, you will have to analyze different sizes of the domain. So that is one thing you have to be aware of in the first place when you start doing your model. Then we have to start with some form of initial stress state. Now, if we are near surface, so that is usually well known, so we will have the vertical stress based on the soil weight, and we will have some form of horizontal stress based on the K0 value. Now, if the soil is highly overconsolidated, then actually we have some uncertainty already in the K0 value, and we very often do not know exactly of how large the overconsolidation was, and that will have some influence on the results, because all our analyses in geomechanics are nonlinear analysis, and so the starting point has an influence on the result. We also have uncertainties in the ground profile and in groundwater conditions. We do have to model soil structure interaction. And here again, all codes will have some different approaches by using interface elements or contact elements. And so you have to be aware again of your way your particular code you're using is handling this soil structure interaction. We have to make some simplifications in modeling the construction sequence, and it's also very difficult to model installation techniques like jet grouting or mixed in place columns, for example. And then most of our problems are actually 3D. And some significant effects we simply cannot capture in 2D. So one of these is stability of a tunnel face, corner effect of excavation, or pile foundations or pile raft foundations. These are real problems you have to do in 3D. Now in practice, we still like to do 2D in many cases for time constraints mainly. And we have invented some ideas how to include 3D effects in 2D analysis, like pre-relaxation factors of tunneling. But again, this will be a decision you have to make when you start your modeling exercise, whether your particular problem is well enough represented in 2D, or you will miss too many details so that it is not worth doing it and you have to go to a full 3D analysis. Now, even if you do a 3D analysis, you will not be able to follow all construction stages in detail. So I have shown 3 examples in here where you will probably go for 3D, but again, you will not be able to model all the steps in your model. And you have to make a decision, what are the important phases which I have to have in the model and which one are not so important, so then I can simplify them. And then we also have to think about the constitutive model. Now, there is no such thing like the soil model. There are different models around, and if you have a certain code, you will have a library of soil models, but they will be different from code A to code B. Now, in practice, still some people use a simple failure criteria like Moore-Coulomb for analysis of serviceability limit states of displacement and stresses, but this is not a very good choice, as I will be showing in a minute. It is, I would say, okay for failure in drained conditions. The next class of models, or the next model which is pretty popular and around for a long time is the modified chem-clay model. It has the significant advantage over a failure criteria that it is a strain hardening model, and this can be successfully applied in some problems like embankments on soft soil, although also we have made in the last decade or so some improvements also on this type of models. Now, fortunately, also in practice, the benefits of using more advanced models are being recognized, in particular for excavation problems. And I will come back to that also a little bit later on. Now, why we still do not see that many of the advanced models used in practice is partly because in usual geotechnical reports we do not find all the parameters. Again, I will come back to this a little bit later. So parameter identification will still be a problem. And then sometimes for the client it is difficult to judge what he gains in terms of safety and costs. I sometimes get a phone call and say, and then a client asks me, if I give you a contract for final element analysis, will I save on the reinforcement in a retaining wall? Well, that's not so easy to say, because it depends on a lot of factors, whether final elements, for example, will give you less bending moment in your wall than a conventional analysis. But of course, as I hope to show you throughout this lecture, I'm of the opinion that you gain because you gain in understanding of your structure, and the better understanding of your structure will inevitably give you a higher level of safety. Now, summarizing these issues we have just recalled, but put them in a very positive context. So I would argue that the advantages of numerical finite elements compared to conventional analysis are that you can simulate the complete construction history. So I have made some restrictions and saying, well, you will never be able to follow all the details, but you can follow the history of excavation or building an embankment or a dam or whatever. If you know and if you want, you could, strictly speaking, also simulate the geological history, at least to some extent. You can then model the interaction with the water rigorously, so you can do a drained analysis, you can do an undrained analysis, you can do a coupled consolidation analysis. You will take care of changing in groundwater table during excavation if you lower the groundwater table, etc., etc. This can all go into your numerical model. You can model complex geometry. At the end, there is no real limit on that. It's just how much effort and how much time you want to put into your model. But in theory, you can do very, very complex models, and you can use, if you want, and you have the respective code, you can use a couple of million degrees of freedoms if you want. But it's not always the case that you need that. So it's still, if you have a lot of experience, you will be able to make a model with a reasonable size. Now, if you use advanced soil model, you can capture important features of soil behavior. So I was mentioning before, there is no single universally accepted soil model. There are different models around, and different models can represent different features of soil behavior to a different extent. And it depends really on your soil conditions, on the ground conditions, and the purpose of the analysis, which of these models will be the most appropriate one for you. We can model soil structure interaction by means of interface elements or contact elements or contact algorithms. But again, there will be some differences in codes. And if we look at failure, I think we have one significant advantage as compared to conventional analysis like limit equilibrium analysis, such as method of slices, where we have to assume a form of failure mechanism and the program then just picks up the one with the lowest factor of safety. But here, when we do finite elements or finite differences, we do not need to specify the failure mechanism. It is an outcome of the analysis. And this is, at least for complex structures, is a significant advantage. So I would say that with all the difficulties we have, the pros beat the cons by far. But we have to realize that all our solutions are approximate solution to the real solution. Now let's have a look at the constitutive models. And what I will do here is I will describe or try to describe classes of constitutive models. And I start with the simplest one, and that's a linear elastic, perfectly plastic failure criterion as the more Coulomb failure criterion, well used in soil mechanics. Every geotechnical engineer knows this. Now, the big disadvantage of this model is, of course, that although it may describe failure, at least in drain conditions, reasonably well, we have a linear elastic material behavior until failure. And this is, of course, not very realistic. Now, the reason why it is so popular is that you need only a very limited number of parameters. But I would argue here that it is difficult or impossible to define a Young's modulus for a particular soil. And that is why this model is not very suitable for assessing displacements under working load conditions, because we will have stress state which are far below the failure stress state, but the behavior will not be linear elastic. I have to mention here that there are other criteria around in the literature and also in certain codes, like the Matsuoka-Nakai criteria, which is describing even failure in drained conditions slightly better than the more Coulomb failure criterion, in particular in plane strain conditions. But unfortunately, these enhancements have not yet found their way into many of the commercial codes. A special case of this criterion is, of course, the Tresca failure criterion, where you put the friction angle to 0 and you put in as cohesion the undrained shear strength. And then you can use this criterion also for undrained conditions, but only in terms of total stresses. This is a very special case, which we usually do not recommend to use in finite element analysis, but you can do it because it's a clear simplification and you know what you're actually doing. Now, as mentioned before, the modified CAM-clay model belongs to the next class of constitutive model, where we have considered hardening. And you see here that the stress strain curve now is non-linear, and an important second issue, which is highlighted here, is that we have on unloading and reloading a different stiffness. So that's a significant difference also to the more Coulomb failure criterion. And again, parameters are very well defined from conventional testing and very well known. And numerically, you would probably add a few other parameters controlling the plastic potential or the yield surface in the deviatoric plane. But I'm not going into detail of that. So that would be, let's say, class 2 of models where we have a yield surface which changes size with plastic strains. The next class will be what we call a double hardening model, and an example here is the hardening soil model. Again, we have a non-linear stress strain curve, and we have different stiffness in unloading and reloading. Now the model here has two yield surfaces. It has a volumetric yield surface and a deviatoric yield surface. Both of them show isotropic hardening. Now this model has become quite popular in recent years, and many codes actually have a very similar form of this model. Some of them have, instead of having two separate yield surfaces, have one continuous one, which is numerically actually more elegant, and but it will do more or less the same thing. Again, parameters can be obtained from odometer tests and triaxial tests, but at the end you will need some form of engineering judgment, usually because they will be not given in the form you require them in standard geotechnical reports. Now with the advanced models, what you can do is you can add additional features like small strain stiffness. That's again very common, and today I think all the codes will provide you with a model which can model small strain stiffness, meaning considering the high stiffness of soils with very small strains and their decay, showing here for an example for the shear modulus against the shear strain. Also, models can include structure if you have a clay, for example, and this is usually also based on modified chem-clay type models, but you could add this to most of the advanced models. I will stop here in describing the classes because, as I mentioned before, I'm talking here about practice, and so I'm not going into models which are available only in research. But just to mention them, of course, we have models which have not isotropic hardening but kinematic hardening, models dealing with anisotropy, and models, for example, placed on hyperplasticity. Some of these models are actually available on the internet, and there is a platform which is given here, soilmodels.info, and here you will find some very advanced models in form of user-defined soil models, and you can then add them to, let's say, Abacus or Plaxis. Now on this slide I will do something which is really dangerous. I'm aware of that, and I expect some criticism on that, but I give it a try. So what I want to do with this slide is to give you an indication what type of model you need for what type of problem. So I have indicated here failure, drained, and this FOS, I mean factor of safety, or undrained in total stresses. Okay, and the important thing is undrained in total stresses. If you do an undrained analysis of failure in terms of effective stresses for a soft soil, for example, then matters become a little bit difficult and are beyond the scope of this lecture. Then I have here monotonic loading on a stiff soil. So with monotonic loading, I mean a structure, a building you put on piles or on a raft or whatever. The same thing on a soft soil, for also an embankment, of course, falls into this class of problems. And then I deal with excavation problems. And here on this axis, I have the models with increasing complexity. Okay, so the simple linear elastic, perfectly plastic one perfectly plastic ones, but with a non-linear part inside the failure envelope, introducing small strain stiffness. Then the elastoplastic volumetric hardening ones, like the modified chem-clay type models. Then elastic plastic double hardening ones, again with isotropic hardening, like the hardening soil model. And then these double hardening ones with small strain stiffness, then here kinematic hardening ones, and finally hypoplastic models with intergranular strains. Now these intergranular strains do basically what the small strain stiffness models do in the elastoplastic models. Now if you look at failure, I said already, you can probably get away with these linear elastic perfectly plastic models under these conditions here. Of course, you can use all the other models as well, but I would say in many cases in practice you would not need that. Okay, but of course they can also produce failure. Now if you look at monotonic loading on stiff soil, you may also get away with an appropriate choice of stiffness with these simple models, but in most cases you will probably have to introduce artificially layers to take into account stress dependence or stiffness increase with depth. You may actually get away when you do a perfectly plastic criterion with small strain stiffness inside. So take into account the non-linearity of stiffness inside the failure criterion. So that may work for stiff soil sometimes. The simple volumetric hardening would probably not be a very good choice, and the double hardening without the small strain stiffness also may do to some extent, but probably is not the ideal choice, because in the stiff soil the plastic volumetric strains will be not that significant, but that is where these models are for. Now with the other models, when you include small strain stiffness and intergranular strains, they will of course also do for this type of models, although you probably may not need them. Now in soft soils is different, because there I would say you will not be able to get any good results with these two simple models. You will need some form of volumetric hardening here, because you will have, on a real soft soil, you will have significant plastic volumetric strains. So that will mean that the double hardening model will also do, but all the further advanced models, of course, as well. Now excavations is probably the most difficult problem within this standard problems in geotechnics, I would say. So I said I won't cover dynamics and these sort of things. Again, for a stiff soil, highly over-consolidated, you may again get away with the failure criterion when you put in a reasonable small strain stiffness model inside. Again, this elastoplastic volumetric hardening, the single hardening one with no small strain stiffness, will not give you very good results. The double hardening one is better, but still, of course, I would prefer really these higher order models for excavations, whether they are in soft or in stiff soil. So the only difference is here that for highly over-consolidated one, you probably get away with this model. So as I said, I'm fully aware that this is a bit of a dangerous thing I'm doing here, but I hope that for those of you who have not so much experience and start doing numerical modeling will give you some indication for what models you should look for if you have a certain type of problem at hand. Now we move on now to the two applications. And what I do with the first one, it's a deep excavation, and we look at serviceability state. And what I will do when I describe this example here, I will point out a couple of decisions you have to make in order to arrive at an appropriate model. And then I will show you on the results what these decisions, what the influence of these decisions is. Now, the first decision you have for a deep excavation you have to take is really whether you go for 3D or you go for 2D. Now, this is an excavation 30 meters deep and 100 meters long. Now, for this one, I would say, well, you will be fair enough to do a 2D analysis somewhere in the center. And of course, you cannot capture what happens here in the corner. The same thing for this one. You won't be able to get anything out for the corner here, but for this long section, that will be okay. Now, if you have something like this, where you have, I will show that in a minute, if you have a sort of quadratic excavation, which you very often have in the urban environment, where you have to make a deep excavation for a high-rise building or so, then it becomes very often difficult to find a representative to the cross-section. Of course, the situation is different if you look at the metro station, for example, which is maybe 150, 200 meters long, and significantly the width is significantly less. Then again, you might be able to find a representative to the cross-section. But as I mentioned, we're looking at this example here. So we go for 3D. Now, what we also have to be very clear before you go to the computer and start modeling is what is the main purpose of the analysis. Why am I doing finite element for this problem? Now, in this case, it's fairly clear. We want to calculate wall deflection because the wall deflection will have an influence on the settlements behind the wall, and these settlements may have or may cause possible damage to adjacent buildings. We want to have bending moments in the diaphragm wall in order to make a design, and of course also in the strut forces. All these under working load conditions. Now, having mentioned here working load conditions, you may use this analysis as well to do a design based on Eurocode 7, introducing partial factors of safety, but I'm not going into detail of how you do that. That would really be probably a separate lecture. But what this means is that a simple elastic, perfectly plastic model is not sufficient. And if you remember the slide I had just a few minutes before, when I was talking about different problems and classes of models, you will realize that I'm much more on the advanced model side for this type of problems. Why is that? Well, the stress parts in this type of problems are not monotonic, so you will have significant changes in stress path directions. It depends, of course, a little bit on the construction sequence, on whether you pre-stress trusses or you have anchors which you pre-stress, and so on. But in general, they are not. Different parts in your soil will follow stress paths which are by no means monotonic. You will have parts which are in primary loading, and you will have parts in your soil mass which are unloading or reloading. And this, of course, invokes different stiffnesses, and the model has to do this. You will have areas where you have plastic strains, relatively large strains probably, but then you will have parts in your domain where you have very, very small strains. That means your decision number 2 you have to take here is the constitutive model. And as I mentioned before, we will go here for a double hardening model with small strain stiffness. That is in line with what I have said before. Now, when we do 3D, what our next question has to be is, can we apply symmetry? Because it may not be obvious in the first place, but if you go for a 3D analysis, you will realize that you will end up with very large models very easily. Now, of course, computers today can do that. You still want to simplify as much as possible. And of course, this again depends not only on the geometry of the excavation, but also on the buildings which are surrounding it. Now, in this particular case, we choose symmetry, and I have to say that this example here is based on a real project, but we made a parametric study investigating a couple of things, and there we then simplified it to allow for symmetry. But as I said, this decision has to be made, but whenever possible, please make use of symmetry, because you can reduce your computational effort. Now, once you have done that, you have to do another decision. And this is what are the relevant construction stages, including changes in the groundwater. Now, of course, it depends a bit on how you construct the excavation, but in this case we have a diaphragm wall, and in most cases in practice actually you will not model the installation of the diaphragm wall. You could, and there are some papers in the literature which tell you how to do that, but I would say in most cases in practice you would do what we call wished in place. So that means you will simply place the diaphragm wall into your model. But that means, and that is what you have to be aware of, you will not have deformations or displacements obtained from your model which are caused by the installation of the diaphragm wall. And of course, whether these are significant or not depend very much on the soil conditions, but also on workmanship on site and other issues. So I'm not going into detail of that. But what you will certainly do is you will specify certain excavation levels you want to have in your model, and that is what you have to provide for. Of course, you have to make phases where you install your struts, probably pre-stress them, and not to forget, you have also to consider changes in the groundwater. Now, in many cases, you will not change the groundwater table outside, or you will not be allowed to do so, but you will, of course, change the groundwater table inside the excavation. And there again, it depends very much on the soil conditions, whether you probably do a flow analysis or you make some assumptions on the groundwater. But you have to think about it and make the appropriate choice in your model. Now, in this case, we ended up with a model like this. You see here the excavation stages, you see the struts, you see the load on top of it, and this gave about 150,000 quadratic 3D elements. Now, type of analysis is the next step, drainage conditions. Again, of course, this depends on your ground conditions, and in particular on the ratio of the permeability of the soil layers in respect to the time you need for construction. So the options are, as the limiting cases are, of course, a fully undrained analysis and a fully drained analysis. Okay, and then what is usually more realistic is a coupled analysis. So you do consolidation during excavation, and one extreme case is also that you do an undrained analysis and then you do a consolidation at the end. So it really depends, as I mentioned, on the soil conditions and on the time of construction, but you have to carefully think in what form of analysis you will have to perform. And then you have another option in how you model the wall. Now we assume here, or in this particular project, we have a diaphragm wall. Now diaphragm walls are, I would say, at least 80 centimeters thick, or maybe 100, 120 centimeters. And that means if you model the wall by a plate element, or in 2D maybe a beam element, what happens is that you basically ignore the physical dimensions of the wall. Of course, you will have an equivalent thickness in your properties of the plate and beam element, but for example, if you have a couple of steep anchors, you may actually have a very high normal force in your wall, and then you miss the base of the wall where you can transfer this vertical force. So sometimes you then get a form of punching in of your wall, as I said, in cases where you have high normal forces, and that may actually mess up your displacement field. So what I actually prefer with these relatively thick structural elements, I try to suggest to model these walls by means of volume elements, just like the soil, and give them properties of the diaphragm wall, of the material, of the concrete. Okay. Now, of course, you have to do some post-processing in order to get the structural forces. Now, there's a second aspect coming in, which works, of course, only if you do a 3D analysis. You may consider, or actually I would even suggest you should consider the wall being an anisotropic material, because remember, we construct the diaphragm walls in panels, and that means you will not have a continuous reinforcement. I will show you later on what the effect of this is, and you see also there are some literature available on this as well. Now, parameter identification. This is a key issue in numerical modeling, and unfortunately this cannot be separated from the method of analysis and the constitutive model we are using. It needs really a good background in soil mechanics and in your model you're going to employ. This is a bit unfortunate, but it is like it is. Now, some codes provide you some form of parameter identification procedures which really help in getting your parameters, but at the end you always need quite a bit of experience and engineering judgment to arrive at a good set of parameters for your particular model. And in most cases you will not get these parameters directly. You will need some interpretation from the available information of geotechnical reports. And usually these reports will never be complete, so you will, in most cases, will have to estimate additional parameters you need for your constitutive model, and of course this again involves and requires some experience. Now, there is a tendency to look at any form of database and say, well, we can get parameters and information from database. I agree that you can get information from various databases, but it is very unlikely that you get real parameters out of it. Now, I have an example here which I presented in one of my presentations on parameter determination, and I said this is what some people dream of. You know, you go into Google Maps, you locate your site, and by some means there is a database where you get the borehole log. Now, actually this is feasible, but then the dream of the numerical analyst is that you choose then for a soil model A, B or something, and then you get the parameters. But please look what I have written here. It does not work like this. So I don't believe in that, although I know that some software vendors try to do similar things, provide database for their models for different types of soil, but I think this is really dangerous, and I strongly believe this should be the issue of the geotechnical engineer who runs the analysis to establish the input parameters. Now, why is this so difficult? Well, first of all, similar parameters have different meanings and therefore consequences in different soil models. This is not very nice, but unfortunately it is like this. And that is again why you have to be pretty clear what your model does and what parameters and what the parameters do in your model. And one of the problems or the reasons for that is that many of our material parameters are not really material parameters. Now, what I mean with that is, as an example, if you have a quartz sand, and if this sand is in a loose or in a dense in a dense condition, then the material is exactly the same. It's the quartz sand, but you will, with standard, even advanced standard models, you will input different parameters for stiffness and strength. So these parameters are actually a mixture of material parameters and parameters which depend on the state the material is in. Now, having said that, there are models around which overcome this problem, but as I said before, most of them are not readily available in commercial codes, and therefore they are not used that often in practice. But I think the modelers work on this. Now also we have limited testing procedures in practice. I'm not talking about sophisticated testing for research, so the stress parts are there limited, which also may have some influence on the parameters. We do have more and more correlations with in situ testing, so that's certainly a field which will improve and will make some progress in the near future, that we get better correlations from CBD, TMT or pressure meter tests where we can get our parameters. I'm personally very much in favor of this in situ testing, but we are far away from doing a CPT test and say, well, that's our parameters. To come to an end on these parameter determination difficulties, it's also in most cases the site investigation is done without knowledge of what is done with the information. So sometimes we don't even know, well, will there be a numerical analysis performed or not, and also of course not which constitutive model to be used. So that means we cannot really design a site investigation program specific to our specific needs of the model, because at the time you do that, you don't know the model. And also the parameters will inevitably scatter within a wide range. That is what we have to live with. That means parameter determination for an advanced constitutive model is not a trivial task. So this again needs a good understanding of soil mechanics and your constitutive model you are using. Now in this particular case, as I mentioned, we use the HSS model, and this is the list of parameters you have to define. And I can tell you, we got this set of parameters. This is an excavation in Salzburg, mainly by back analysis of structures where we had measurements. And we back analyzed these excavations, and from these back analysis over the years, we actually came up with a decent set of parameters for this type of ground conditions. So I'm not going into further detail of that. Now, what you can do sometimes, and what is an issue if you do an undrained analysis in terms of effective stresses, which you should do, then of course if you have undrained triaxial tests, what you can do is you can back calculate the undrained triaxial tests with your soil model with effective strength parameters and see what undrained shear strength your model predicts for a certain stress path, let's say triaxial compression, extension, simple shear, or whatever you find relevant for your problem. So that is actually what you should do, because obviously in a constitutive model in terms of effective stresses, the undrained shear strength, which is by no means a parameter, is not an input. What also helps if you have pressure meter tests, you can back analyze the pressure meter test, and also by means of this back analysis you can optimize your parameters. But this of course is a boundary value problem. You have to model this as a real boundary value problem and try to fit your test results. Now what do we obtain now as a result? And I have mentioned before that I will show you the influence of certain modeling assumptions. Now this here is the first influence on the drainage conditions, and what you see here, this is the wall deflection for the undrained case. These two are the different coupled cases, and this is the drained case. Now of course this is what you expect. The coupled one is between the limiting cases drained and undrained. And again, you have to make the decision whether you make it simple and say, well, I can live with the drained one, overestimating my wall displacements, or you have to go for a coupled analysis. Please note that doing an undrained analysis with a final consolidation step does not give you exactly the same result as a drained analysis in the first place, because the stress paths you follow will be different. And of course, you will also have differences then in the bending moments. Now this slide shows you the interface, the influence, of the modeling the wall. The blue lines here is the comparison of modeling the wall as a volume element and a plate element for isotropic modeling, and the green ones is again the difference between plate and volume element for anisotropic modeling. And you see that you have some influence on how you model the wall on the deflection. So you have to give it some thoughts what you use. And here is the difference in whether you model the wall as isotropic or anisotropic for different drainage conditions with the volume elements. So again, you see that, for example, on the drained conditions, the differences between isotropic and anisotropic wall modeling is quite significant. In the undrained case, it is not so. And here the geometric representation. So you will see here that this is the 2D analysis, and of course you see that you will overestimate the displacement significantly for this particular case, which is not surprising because it's a square excavation. But you see here that if you model in 3D the wall anisotropic, you come closer to the 2D result, and that is of course also reflected in the settlements behind the wall, where you get significantly larger settlements in the 2D case. Now this may not actually be on the conservative side, because depending on the structure you have here, you may actually get higher gradients on the surface settlements if you model it with 3D. Now here's just to finish this part. You see here that this is what you usually get. You get the vertical displacements behind the wall, with the advanced models. Now, if you use an elasto perfectly plastic models, you sometimes get heave behind the wall, which of course is by no means realistic, and that should just emphasize again that you need a higher order model for that. Now, evaluation of results. There are different ways of doing so. One way is use simplified methods to get an order of magnitude, or you can also go into the literature and look on some data which is published there. And one is, for example, a database published by Long, which is based on Clough and his co-workers, where they plot depth of excavation on this axis, and here's the maximum horizontal displacement divided by the depth of excavation in percent. And you see here that this example follows in here, and you see that a lot of excavations fall in this 0.1 and 0.2%. So this is just to emphasize that critically assess your results. Try to have some means how to evaluate whether these are correct. Now, quickly on a completely different example, this is a geotextile reinforcement embankment on the slope. So this is a widening of a road here, a connection here. This is the original slope, and there was an embankment built on here. Now this embankment failed, and the purpose of the analysis was now back analyze the failure scenario, and based on this back analysis establish probable strength parameters, and from there assess the effectiveness of reconstruction measures and calculate factors of safety for various stages of reconstruction. So in this particular case, a simple elastic perfectly plastic model is sufficient because we are not looking at displacements here. Now that's the situation, so that's the model. The average inclination of the original slope was 34 degrees. Then the embankment was built on there. It failed at this level. And then this was the reconstruction, so they moved the embankment towards the back, put in some anchors. Now ground conditions was a sort of sandy gravel, weathered rock, not always clearly identified. But the interesting part was that the geotechnical report gave strength parameters 40 degrees and 0 cohesion for this. Now what happened? Now if we analyze the situation at failure, and we did it by different means, again remember I mentioned just try to back up your analysis with some different analysis by different means or good estimates or experience, whatever. So if we did it here with finite elements with the so-called strength reduction method, and here we did it with finite element limit analysis. Now what you see is if you do finite element limit analysis with an associated flow rule, so that means we take the latency angle to friction, we get a factor of safety of around 1.2. Now if we do this with a dilatancy angle of 0, we see that we actually get failure. And if we take 10 degrees of dilatancy, this is a bit conservative maybe, but this is probably more realistic, we see that depending on the cohesion we take, we kept the friction to 40, you get actually factors of safety around 1, so that means failure. Now the original design was on limit equilibrium, and you see here you got 1.2 factor of safety for this particular situation. So this was by no means conservative, and you will also realize you get similar numbers as if you would get with a finite element limit or finite element analysis using associated flow rule. But I hope you will agree that nobody would actually use an associated flow rule for this type of problem. And then of course you can do the analysis of the final stages after reconstruction, and you see again, I'm not going into detail of this these modifications, how you can do finite element limit analysis with associated flow rule by modifying your strength parameters. So I have not time to go into detail of that, but what I want to show here with this example is that compared to limit equilibrium analysis, the finite element analysis was able to actually capture the failure situation, and that if you use two different methods, you get very different results, very similar results, sorry, and that means you can be quite confident about the validity of your calculations. Now some final remarks. What are the objectives of numerical analysis? Just to summarize up, of course, we want to do some quantitative predictions. Sometimes we want to have checked alternatives of design. So you may have one design and another, and you may see whether they are equivalent in terms of displacements, etc. So you can check design alternatives. You do back calculations. I mentioned that, very helpful in getting more experience under certain soil conditions. And the key thing I would say, and I repeat what I said at the beginning, is understanding. Try to identify critical mechanisms, try to identify key parameters. That's powerful, and what you can do with numerical methods. And of course, I also mentioned that be very clear what the purpose of your analysis is before you start modeling on the computer. What should you consider? Of course, you have to make the model as simple as possible. I mentioned that also. Don't go into very, very detailed models, but you have to be aware of what you simplify and what you cannot simplify. That's really the experience you need as a modeler, that you put into the model what is essential, but forget about things which are minor details and change the results by a few percent. You have to select the appropriate constitutive model, of course, and this is also something I want to point out at the end. Pay attention to patterns of behavior. So try to model the system behavior and not a particular value of displacement. So try to get everything right, reasonably right. Deflections, settlements, stresses in struts, etc. Perform sensitivity analysis. Check the robustness of your solution. So what you should do is that you change a parameter and run it again and see whether the global behavior is very similar. Of course, numbers will be different, but the system behavior should be the same if you make a small change in your parameters. If it is not the case, then be careful and go into detail and see what the reason is. And of course, model calibration should always be done by whatever means which are available. So that could be experience of a senior engineer in your office. It could be a simple analytical solution. It could be a database, etc., etc. But try to make sure that your results are reliable. Okay, and this also mentioned already. So I will finish this presentation with a few quotes. Geotechnical engineering is complex, and it is not getting easier when you use the finite element method. Actually, it gets more difficult because on top of all the soil mechanics, you have to understand finite elements and in particular the constitutive model. Now, of course, you need a good program, but don't blame the program if it doesn't give you correct results. In most cases, I would say almost in all cases, it's the user who is responsible for the result and who is the one who makes the mistakes and who is the reason for getting nonsense out of the result, which is actually very easy to do by doing some not correct modeling assumptions or even some stupid mistake in input parameters, etc. And of course, the design in geotechnics is considerably more than this finite element analysis. Now, I borrowed these quotes from Gino Vigiani. So finally, I would say that if properly used, numerical methods are a powerful tool with significant advantages compared to conventional analysis, and I hope I could show that in this lecture. but the keyword here is properly used. So this is my final advice. If you do numerical analysis, make sure you understand what the program does, what your constitutive model does. Think about your modeling assumption. Think about your parameters you put in, and don't use it as a black box and say, well, the computer has said that this is the result. You have to be sure that you believe the result you obtain. And then with some acknowledgement and some suggestions for further reading, I would finish this lecture, and thank you very much for your attention.